suppose we're interested in a very basic question. I mean, what is the average delay of United out of San Francisco? Okay. To answer this question, it would be awesome if we knew the population distribution, if we had all of the information from United. Okay, and we could then say, okay, the average delay is this, because we could exactly calculate it then, right? But we don't have all of that information. We're not working for United. We only have 100 flights or 1,000. We have a sample. So the natural thing that we do is we calculate the average or the mean of that sample, okay, of that 1,000 flights. So this is called the sample mean. Now, our sample isn't the population. There's some differences there. Okay, you might even call them errors. Okay, so whenever I calculate the mean of the sample, it's not going to be equal to the mean of the population. The question is, how far away is it? Is it close? Is it accurate? We can actually say a lot about that. So let's take a look. Here's the population mean. Okay, this is if United sat down with their full data set and calculated the mean. This is not a random number. If I do this again, I'm going to get exactly the same thing. It says the average flight delay, the mean flight delay, was 16.65 minutes. Okay. Now let's look at our sample. So I take a sample of 100 flights. I get the delay and calculate the mean. So I run this. Remember, we saw the actual answer, right, is 16.65. Here's my guess, 19.37. So you see, I'm not exactly right. I'm off by 3 minutes or so. Okay, but the important thing here is that this answer, this mean that I calculated from the sample, is a random number. If I rerun this cell, what it's going to do is it's going to go out, get a different 100 flights randomly, and I get a different answer, 11.86. I do it again, I get 15.36. I get 22. I get 20. I get 13. Okay, I get a different answer every time. Now, sometimes you might run this and you get pretty close, 15.36. That's a minute off. That's not too bad. But then sometimes you run it and then you get something that's, way off, like 21. Okay. In practice, you're not going to go out and get a bunch of samples. You're going to get one sample of 100 flights maybe, and then call it a day. And then you get a number back and you don't know how close that is to the right answer. Okay. So what we're going to be able to do is give you some way of telling giving you confidence, or a sort of confidence interval that tells you how close you might be to the correct answer based on the size of the sample. So the key point of this slide is that because the sample is random, the sample mean, meaning the mean of the sample, is random too. It's a random number. So what we could do here intuitively is we could increase the size of our sample if we want to be more accurate. So let's crank it up to 1,000. Okay, so now I'm at 14.71. I get another sample, I'm at 15.89. I keep doing this. What you might notice is that my answers here are not changing too much from run to run. I'm usually getting around 16, sometimes 15, sometimes 17, sometimes even 18, but I'm never seeing 21 like I did before. If I really crank this up to like 10,000, I'm going to stay pretty much in the mid-16s. Okay. The idea is that as the size of the sample gets bigger, the sample mean is going to get closer to the population mean. Okay, so let me unpack those terms again. Remember, the sample mean is the mean flight delay in my sample of flights, of like 100 flights. The population mean is the real mean of all of the flight delays. It's what United can see, and it's not a random number. So let's try this out. I'm going to increase the size of my sample from 100 all the way up to like 10,000. And I'm going to calculate the mean of the sample. And you can kind of see that it starts bouncing around whenever it's small. Remember, these are random numbers. So if I do this again, I'm going to see a different thing. Okay. And then, but as I get closer, as I make the sample larger, my answers are all kind of in the mid-16s. So again, one of the important things here is think about how this is done in practice. I go out, I get my sample of 100 flights, I calculate the sample mean, and then I report this as the average flight delay. But how do I know that that's actually close to the right answer? Intuitively, the larger my sample, the more it's going to look like the population. And so it'll be close to the population mean. But I want to sort of quantify how good it can be. If the sample is small, there's a good chance that the sample mean is bad, that it's far away from the right answer. If the sample is big, there's a smaller chance that the sample mean is bad. Here's kind of a picture. Suppose I take a small random sample and I calculate the mean. The right answer, the population mean, might be here, okay, in this cartoon. But what I find is here. It's far off. I calculate another sample mean, I get this. Okay, so I get a bunch of different samples. Their means are kind of scattered around. They're not all that accurate. This is just a cartoon. There's no two-dimensional aspect to this problem. Okay, but as I create a larger random sample, then all of my random samples, I still have random numbers, but they're all kind of bunched around the right answer. So basically, I'm more confident that my sample mean is close to the correct answer, the larger my sample is. So because the sample mean is a random number, we can ask about its distribution. This is where things get a little bit maybe confusing because you have distributions on distributions, okay? But it's not totally out there, okay? What we have is a random number. It's the sample mean. And I could do this again and again. I could draw a bunch of samples, record the mean of each sample, and then look at the distribution that I get back. So let's try this out with a bit of code. Let's take a look. I'm running 2,000 experiments. In every experiment, what I'm doing here in this line of code is I'm computing the sample mean. Compute the sample mean. Okay. I compute the sample mean for a sample of 1,000, size 1,000, and then I add it to an array. And then I do it again. I select 1,000 at random. I take the sample mean and add it to an array. So at the end of the day, I have 2,000 sample means. So I plot the histogram of this, the distribution, and this is what I see. So this distribution shows me the results of my experiments, that I ran a bunch of experiments here. Now in practice, I would usually only do this once, remember. I would only run one experiment, but here I did the experiment 2,000 times. And what I see is that most frequently, the result was pretty close to that red bar. The red bar is the population mean. It's the right answer. But sometimes my experiment would be far away. So sometimes my experiment would give me a sample mean of 20, or sometimes it would give me something like 13. Okay, so it would be pretty far away, but it looks unlikely. Okay, the most likely results are in the middle here, and the distribution shows me that it's unlikely to see anything this high. Let's change the sample size. Okay, so remember, I did this sample of 1,000 flights, and I did that 2,000 times. Let's decrease the sample size. So suppose now I only selected 100 flights. What do you think would happen to this distribution? What do you think would happen to this histogram? So take a guess. I'm going to run it right now. Okay, and here's what you see. The distribution gets wider. Sometimes I'm seeing sample means out in 30 or even like 33, way off, right? And that's because my sample was small and I'm just getting unlucky. Okay, but as I increase the size of the sample, the distribution becomes narrower. It becomes sort of a narrow band around the correct answer. Here's what this means in practice, okay? In practice, again, I'm only going to run one experiment. I'm only going to get one sample. What you're seeing here is 2,000 samples, but I'm only going to get one. Now, when I get that one sample, I don't know where I'm at on this picture. I could be all the way over here. I have no way of knowing. unless I got another sample and kind of did this over and over again. I don't know. But what I do know is that if my sample size is really large, say 1,000, it's really unlikely that I'm far away from the correct answer. I'm still somewhere in here and I don't know where I'm at, but this is narrower. This blue histogram is narrower, and so everything in it is closer to the correct answer. So if I were to really crank this up to like 10,000, you would see it get really narrow around the correct answer. So that's the idea behind taking larger samples. It's the idea of the law of averages and converging to the right probabilities. Okay, so let's take a short detour here and take a look at a particular subset of our data. This is an example of a case where we're going to take a sample. It'll be a random, random sample, but it won't be uniform. What we've been doing before is we took uniform samples of all of the flights, okay, meaning that every flight was equally likely. But in this case, what I'm going to do is I'm going to take a uniform sample of flights from Denver, and only from Denver, okay, or I guess to Denver. I think the destination is what we're looking at here. Okay, so this is a probability sample. Let's look at the distribution. So I'm randomly selecting 100 flights from San Francisco to Denver. I'm doing that 10,000 times. So I'm repeating that sample over and over and over again and plotting the distribution. And here's what I get. So the red is the mean flight delay of all flights, not just Denver to Denver, of all flights. Okay, but what I see here is that the distribution for delays to Denver is skewed, it's biased. Okay, it's most likely that the delay is around 12 or 13 minutes. And if I increase the size of my sample, this bar or this histogram here is going to get narrower, but around the incorrect value. Okay, it's going to get narrower around like here. Okay, so what this demonstrates is, if I'm interested in the average flight delay, regardless of destination, and I take a sample which is not uniform, which is like looking only at flights to Denver, for example, this whole thing kind of falls apart. I'm not guaranteed that I'm going to converge to the right answer as I increase the sample size. So another example here is I'm going to take an evenly spaced random sample. This is what I said before. I pick my first row randomly, and then I take every 10 rows after that, or every 50 rows in this case. I'm going to do that, compute the histogram. Let's take a look and see what we get. Okay, so I see a histogram where I have sort of gaps here between flight delays. Okay, so I don't see any flights here between 10 and or between like 11 and 13 or so forth. Let's increase the size here. Let's make a gap of 20. Let it run for a second. So what you're seeing here is the fact that we're not getting a bunch of data in our sample because I'm taking every 20th row, and so that means I'm taking like 1 out of 20 rows in my data set, which is really making it sparse. Okay, so that's why the histogram kind of looks like this. Okay, so lastly, what if we took the distribution of means from repeated samples of the first 100 rows? Okay, so this means I'm really decreasing the size of it's not quite the population. Basically, I'm saying let's decrease the set of flights that I can possibly sample from. Okay, so what you get here is a very high bias. What this means is that my distribution, okay, is always sort of off because I'm not looking at the full data set. Okay, I'm looking at that first 100, I compute the sample mean, it's always going to be the same. So I'm going to get something that's always pretty off, but it doesn't change that much because I'm always looking at the same sample.